So then we can start first session for this course, which is called Introduction to Knowledge Society Technology. This, I believe, is code for it, and that, I believe, is time when it is conducted. And to save network bandwidth, I will stop video. What is general information about this course? In size of work effort, it is counted as 4 credit points. So not the biggest course in the world, but also not the smallest one. And contact time from teacher is supposed to be 64 hours. I believe these are academic hours. Somebody says that sound is very weak. Let's continue. And it is assumed that contact time for this course is 64 academic hours, so it's 45 or 40 minutes. And your homework is 96 hours, which is a little bit more than full working week. Little bit more than 2 full working weeks. But if you will be successful and lucky, probably you will be able to shorten this time, because if you will know what to do in these practical exercises, these are not supposed to be very hard. And originally, course materials for this course in Riga Technical University was put in this moodle.mii.lv, but as far as I know, probably later these materials will be updated and put into a different tool somewhere else. And I will tell you this later, where you will find these materials for course. Probably next week we will have more precise information. But what we know for sure is that presentation materials and ideas, what you should learn here, are from other universities where they conduct similar courses, and these are mentioned here. And because for me as a teacher it's easier to reuse some other related materials in other courses I have conducted in other universities, sometimes I will reuse my own materials as well. And who I am, my name is Valdis Vitoļņš, and I don't mind if you say it English Valdis Vitoļņš, because with non-diacritic letters, using only Latin letters, that's how it's pronounced in English. And I work as IT freelancer in my own company called Odo.sia. And if you are curious, you may look on my official history of my work experience in my website odo.lv/valdis_vitoļņš_cv. And my email for contact is valdis.vitoļņš@odo.lv. And because surname Vitoļņš is quite popular in Latvia and name Valdis is also quite popular, there are several people still alive in Latvia who have the same name and surname, and probably the easiest way how you can mix me up with somebody else is another Valdis Vitoļņš, who is chairman of Executive Board of Jūrmala City District Heating Company, and he is also teacher in Riga Technical University. But as far as I know, he teaches about heating systems and thermodynamics in general, not about general course in computer science. And another guy what I have mixed up is Valdis Vitoļņš, who is desktop designer at other company and who is quite popular if you search for him about different kind of hiking and such kind of entertainment. So, and before we go into first topic for this course, do you have any questions or comments to me about this course or about myself or about whatever? It depends. In general, Riga Technical University, their official policy is that crisis of COVID-19 is ended, and as usual, these courses should be held when contact hours happen. They should be in premises of Riga Technical University. But because their requirement was that every student should also give either this COVID certificate or negative results for the COVID tests, and not everybody could prove this, at least initially here. We start with remote course, and I don't know how that will happen in future. And hopefully you will be timely notified when this will be expected to be on premises of Riga Technical University. But in general, what I will try to do is I will make records of all these sessions, and you will be able to listen them and review them on whatever time you can manage to do this for your free schedule. So, in general, I don't know. Maybe one half of these contact hours will be held in some premises of Riga Technical University, because for some reason they are very proud of their computer classes, and they think that it will be easier to you to do your practical exercises in their classes than in your home. I doubt it, but if their policy will be that we have to use these classes because they have these, then of course we will do this. So that's my answer. An answer in general is that I don't know. Anything else? And by the way, if we will be in room in Riga Technical University, probably I still will broadcast this in this Zoom session, which will be used for these sessions. And if it will be easier for you, then you will be able to do it remotely. I think that will be my approach. So I will not go against general policy of Riga Technical University, that if they will say that we have to be in class, at least I will be in class, but I will not make artificial obstacles to you that you can't handle this course successfully working remotely. Any other question or comment? That's because group is bigger than students can fit into a single computer class. And so if we actually follow their general policy, we actually need to either do it in two different streams, or we need to book two different classes somehow and then manage this again through the internet like remote work into different classes at once. So that's one of reasons why I particularly am not very for office hours in Riga Technical University, but yeah, I will not go too much against their policy. But I hope that you will be able to know this in more details later when time will come up. Hopefully timely, not in last minute. So my preferences is that I think your computers usually are not much worse than these computers on classes, and if you are not looking on this meeting through your mobile phone but through real computer, then probably in this particular course you will be able to manage everything with computer you have at your disposal. Anything else? You can do it later. First, I think that we are talking about the same system. I registered to this system only today, so I'm not using it for now. But don't worry, you will be able to get materials of this course anyway. In any system we will decide to use for this course. So in general, my plan is that you will be able to go through this course remotely using one website or another, but so your quality of life shouldn't be much worse if you will not be going to an office for these contact hours. And yeah, by the way, here I have my own website, odo.lv, where I have shared other training materials for other courses I have held for other universities and things. So if it will be easier for me, I will just point to some place on my website where you can get all these materials. But I think that I will figure it out how to do this at least till to next session. Okay, so I'm now looking on chat. Does this say something new? So hopefully we will manage to do it in more efficient ways, that we will not need to do repeat for practical exercise or whatever on two different streams like the same course but for different groups because of physical limits. And because of RTU requirements, they want to do this in their way, which I think is not the most efficient way. Probably we will be able to do this as a single group for all the students in the class, either because some of you will attend it remotely, some of you will attend on class if will attend, and that these who will attend in class, I hope that you will fit into a single room. So, any other questions or comments before we start the first topic? I can't answer. I think that all of these sessions definitely will be for 4 hours. That means if we will do it as a single group, then probably we will not so stressed to rush ahead for these practical exercises. And if you will be able to do it quicker, then you will be able to do it quicker. As I told you, here for these 96 hours, it is worst case scenario. Idea here is that everybody should be able to do practical exercises in that time, but these who will have better skills and better knowledge how to do these things, you will be able to save time. So that's about practical exercise. But in more details about practical exercise, we will go into next session. In general, my personal plan is, it may be adjusted, is that we will talk about practical exercises each second session during these contact meetings. So for today I will mostly cover just different theoretical aspects, but in next meeting I will also talk about some particular practical exercise, and in general there will be 8 different topics for all these practical exercises, and it's planned that there are approximately 16 meetings in this course, so each second meeting will be also about practical exercise as well. So I hope that I covered all the most important issues, and now we can start first. Hopefully easy topic about computer history. By the way, can you tell how many of you have not technical training background in some for bachelor's degree already? For example, how many of you have not studied in high school, actually, in university, because Americans say that high school is what we call in Europe secondary school. Or so, who of you have not studied anything about computer science yet? I see from chat quite a lot of you have. Okay, so hopefully this will not be hard topic for you. If we will have enough time, we will go also in some of basic mathematics as well. And if we look on history, then of course computers have very long history depending on what you call a computer. For example, 100 years ago, computer or calculator was person who did computing or calculations for some other person. So they just used it as a outsourcing to do different kind of mathematic operations. And if you call any device which is intended for some kind of calculations or computers a computer, even though it doesn't use electricity, it's not connected to the internet, etc., then of course the earliest devices used for computing were these abacus devices, and probably you have not seen these abacus devices on shops, but when I was child, that was in former Soviet Union, and because former Soviet Union was not very advanced and electronical computers at that time, in many shops these abacus devices were still used in shops, and I actually learned how to use them, how to add and how to carry on these things. So in general, this is old school abacus. New school abacus is, maybe I can find out. So that device was using decimal system for counting, and in general, how this work? It's positional counting system, and you add numbers here and carry on. For example, if you have 10 here, and so first you put everything to the left, and then you, for example, add 1 here for like, let's say, cents, and here are, let's say, euros, and then you add here some more, and then when you carry on, you add more and more digits here. So even though Abacus as device is thousands of years old. Even, let's say 30 years ago, such devices were quite widely used. And these devices, of course, could be used only for positional numbering system, which means that each of these stones in slits or these things on, let's say, strings represents how many of possible digits you have in each particular position. And of course, like antique Romans didn't use abacus because their numbering system was not positional, and therefore their calculation was much more complicated. And also don't be confused here that everything here is about calculations and numbers, because even though today we are using computers for many things, editing pictures, sounds and multimedia, and chatting and writing, etc., everything is just number internally, and only meaning is different, and only rules how we deal with these numbers are different depending on what particular format we are using to store these numbers and to calculate them. And about details here, I think we will go later in next session after 1 week. But so don't be confused that we start with simple calculations how to add and subtract numbers when we look into history. Because if you look internally how your computer works, it still just adds, subtracts and multiplies, maybe divides numbers inside it. And then later, of course, when more precise mechanics was available, these devices become more complicated, so you could do these calculations just by pulling different, so your calculations become more mechanical. And so all these devices started to develop many hundreds of years ago, and together with such more sophisticated mechanical things, also theory about ideas, what is possible to be calculated, evolved. And probably the first pioneer who thought about theory behind these calculations was Charles Babbage. And what he didn't manage to make real devices out of his ideas, but what he introduced is thing which may be general purpose calculator. So if you look on these early ideas, all these devices couldn't be used as a general purpose machines. Their algorithms, what they could do, were built into their mechanics. So if it was built to add numbers, then you could only add numbers. If it was for something else, then of course its internal mechanic was completely different. But Charles Babbage was one of these guys who decided that in general you can also make these devices programmable, so that if you change some switches somewhere inside it, then you actually can change what your device actually does. And later it was built from his descriptions and blueprints, so-called difference engine, which was used to calculate polynomials, which are used, for example, to multiply numbers, etc. But this device was actually built in modern era when more precise mechanics and construction was available. And what was legacy from this guy, Charles Babbage, was that these were first ideas which introduce this idea that some device may be not built only for single purpose, but that you can actually create more general device which may be used for different purposes depending on how you change its internal structure. Of course, for mechanical device it means you switch different gears and levers, etc. But in modern computer, of course, that means you just switch these levers and gears inside its chipset in its electronics. And then Augusta Ada King, Countess of Lovelace and daughter of Lord Byron, was known to Charles Babbage, and she also was quite bored of her everyday life, and she started to write different kind of programs for this engine, which was only on paper, for the Charles Babbage analytical machine. And so that was a few hundred years ago, and it was quite close to what I did when I studied for my bachelor's degree. We also couldn't get hand to real computer because Grove was too big for everyone to get access to real computer. Of course, that was IBM PC at that time, and I will explain later what IBM PC means. But idea was still that we knew how to program this machine, and we wrote programs by knowing how this machine should work, even without access to physical machine. And so therefore she is considered the first programmer in the world, and only difference is that all programs she wrote for these algorithms to do different calculations were just for hypothetical device which was described by Charles Babbage, but which was actually not built until modern times. And also I have seen this device as well. It was also still used in Soviet era in Latvia. It is simple calculation device to add and multiply numbers. So here you put different positions of your decimal numbers. Again, there is some fractional part and other. And then you rotate it once, then you add another number, rotate it once, and then you get the sum of these numbers. So this means you can put one number here with these gears, and then so-called add it, and then you put another and add it, and you read these values here. If you needed to do multiplication, you could do this, but to not get lost in many multiplication operations, here it also has this counter of number of rotations. For example, if you do this dumbly and need to multiply 3 by 1000, then you put number 3 here, and then you rotate it 1000 times until you see that here 1000 rotations were done, and you see result here. So again, purely mechanical device, still was used before early computers. And then there of course were different kind of other pseudo computers which used mechanical gears just to add. For example, here it is just carrying out numbers. For example, when you have 9 and you add 1, this gear becomes 0, but this gear next becomes 1. So you carried on this first digit to the first decimal place after that. And then of course there was these logarithmic rulers where you can add logarithms of numbers, which means you actually multiply numbers when you get logarithm back from these numbers. But these were analog devices, not digital devices, so these were not very precise. So if you are curious, I also had one at my home when I was learning in secondary school, but we will not talk about these devices because these devices are analog devices. They are not very precise because here, if you want to multiply 2 by 3, you put this ruler and you see that here it's a logarithmic scale, so it's stretched more and more and more, and then get 3 in this another ruler and see somewhere here on 6, but because it's analog device it's not very precise. And of course, if you want to do this with analog operations, your ruler should be much bigger to get more precision out of it. So that's about analog devices. And then real changes happened when these arithmetical devices changed from mechanical gears and levers and pegs to electricity, because electricity can work much faster than actual gears, and therefore real computers took off and their development took off when first electrical computers were created. And one of fathers of these electronical devices is Claude Shannon. Shannon is famous for his Shannon criteria, for example, how you can extrapolate digital signal into analog and back, and about sampling, and we will go into this later when we will talk about with audio editing. And then Alan Turing was a guy who actually participated in building first electronical computer using vacuum tubes. So vacuum tube in general is just a switch, and for example, switch can be either closed or open, and here is some lever, and you can also close it, and then it's closed with this lever. And for this vacuum tube, it works in such way that here is transmitter and here is receiver, and here is this signal which either allows electrons to go through it or not. So it is in vacuum, and this transmitter is hot. And if it's hot, it emits also electrons, because in metals electrons are very loosely coupled, so they just bounce around here. And if you add positive electricity here, these electrons are repelled, and so this switch is opened, so now current is going from here to here. But if you add negative polarity here, then these electrons become faster, actually vice versa, because it repels. So minus here, it repels electrons because electrons are minus, so they are here and current is not floating, so it's open. But if you add positive electricity here, charge, then these electrons are bewilkt, repelled, and so these electrons are going through this, it's something like a sieve, and then they go to this electrode and current starts running through here, and then it's closed. So that, and then you can build devices using these tubes, and one of first was created is this Colossus machine. And this Colossus machine was used to crack electromechanical device called Enigma, and it was used to encrypt messages for Nazi army, actually for their submarines. So in theory it was very secure. In practice they have one serious flaw, because with this device letter A was never encrypted to letter A again, so it could be encrypted to any other letter except letter A itself. and that was a serious design flaw, and it was used to crack this device. But this cracking was done using brute force approach. This means all these possible combinations, which were not so many as Nazi generals thought because of this design flaw. In general, it means it has security or encryption weakness. And so this device was cracked by this machine called Colossus, which used just the brute force attack. It used all possible combinations to crack these codes, and so it was run every day to get new code what was used to encrypt messages from these Nazi submarines. But this was still not general device, but purpose-built device. Its only reason to be was to crack these Enigma codes. But later, International Business Machine Company created first general purpose computer, which actually could do different operations depending on how you programmed it. And how early programming was done. Early programming in general was done changing switches into memory part of this machine. So that would be, for example, in modern programming language, it would be something like assembler. I will show it in details, I think, in next week. So when you put these switches in one way, it did, let's say, multiplication of two numbers, and if you change the switches in different way, it did adding these numbers. So remember, all these devices are very primitive comparing to modern computers, and therefore all these operations, what they usually could do is just add, subtract, multiply, etc. And of course, you can describe any operation like generating primitive numbers or whatever by series and iterations of the same primitive operations, subtract, multiply, add, etc. So, and that was after World War II, and then when they started to build these more general purpose computers, which could be reprogrammed with these switches, one of another pioneers who improved this design of general computers was John von Neumann. And what he introduced, it introduced the idea that everything for a computer is just data. Data which you handle are data, and program which you execute is also data. So he mixed up this. So initially, for these purpose-built computers, algorithm and data was completely different thing. For example, if you look on this Colossus or Enigma, so algorithm, what they do, was built into hardware, and data, for example, code to crack, was this data as an input, and then data as an output, for example, cracked code, for example, a number. And that was for these specific purposes built computers. But John von Neumann introduced this idea that if you have general purpose computer, then what you can do actually is following, that before you load data, you actually load your program or algorithm, and then you store it somewhere and you modify how exactly this hardware will behave. And then you continue to do other data, to do actual calculations. And that means that you can use memory for computer to do both. First, to describe your program, and first to do actual data. For example, if you want to generate primitive numbers, then first you load some data which will do this Aristotle sieve or whatever algorithm to provide these numbers. Then, of course, if you generate these numbers, you don't need to add any data as input, and then it produces, let's say, 1, 2, 3, 5, blah, 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 as an output for all these iterations. And so this is actually bars of general purpose computers that if you create your hardware general enough that it can read what to do next from its internal memory, not just from hard-coded switches and gears and pegs, etc., then you can actually allow your computer to do many different things depending on what kind of program you load before this data. And so, in general, this von Neumann architecture looks like following: that you have this central processing unit, which can do different kind of operations with your numbers. And then you have internal storage or internal memory. And then you read your program first from your input. And your input may be different kind of inputs. For early computers, this was punch cards, which you punched actual bits to read them. And again, if you are curious about and I used punch cards when I studied for bachelor's degree to use it as a notes paper, like what are today these sticky notes. But what is bit here is this hole created into this punch card. So you punched holes here, and it means what it's not punched, it's I think 0, and if you punched it here, it is 1. And you got these small paper bits here punched out of this card, and that's why it's called bit, because it's a small bit of paper punched out of this punch card. And of course, if your program is longer, then it can fit into single punch cards, and you have stack of such punch cards to read one by one, and then they slide here electrical contacts over this to read these bits one by one. So you read this either from punch card or from your hard disk from your computer, and one part of this input data is stored to use as a description of your algorithm what this processor should do. That's your program part. Similarly, as you load Microsoft Word first to edit your Microsoft Word document, and of course you can double click on Microsoft Word document, but it still takes time because first your computer loads specific program to edit this document, this data, and then it starts executing it, and then it starts handling this actual data, what you need to do. And particularly for computer, and there is one big weakness for this architecture, because it's general purpose computer and it can do whatever you like, and there is no strong difference between data which you execute as a program and data which you handle as an input. For example, your Word document, you can create different kind of computer viruses, because this computer virus may look like a just Word document, but internally it actually says do execute such instructions and such instructions, etc. But still, all computers work with this approach because this is the best approach how you can build general purpose computers. So everything is just data. Only difference is that some of data you execute as a program, but some of data you actually handle as a data and do whatever you like with this data. And then one of early pioneers, particularly for programming computers, was Admiral Grace Murray Hopper, and she was first who invented compiler. And what is compiler? Compiler is program which converts text into numbers which are executed as a program. So for this one name and architecture, you just read numbers. Numbers in, and if this number says execute starting from this number, then of course it will execute starting from this number and maybe some numbers out. And if you are tired of just writing numbers like 1, 2, 3, 4, 5, 7, blah blah blah, to program your general purpose computers, you may decide, wait a minute, because it's very hard task to do for human to do these numbers, let's do something similar. Let's say add and save and subtract as a human readable text, and then convert these numbers as instructions to processor. And if you put this text, these instructions into compiler's input, and it provides these actual instructions to be executed in your CPU, then it's compiler. And if you are curious, actually you can search for this lady in YouTube. She has quite a good lectures in YouTube about early history of computers. So here are different kinds of these vacuum tubes. So size here is, these larger ones are few centimeters, this smaller one probably is less than centimeter in height and probably more than centimeter in height. So how fast they could go, or usually clock frequency for these computers built with vacuum tubes was some kilohertz. And you should know C units to work in computer science like kilo, mega, giga, tera, peta, exa, zeta, iota, 1000 times more and more and more, and milli, micro, nano, pico, femto, opto, zepto, yocto, 1000 times less and less and less. So modern computers work with clock frequency approximately 3 gigahertz, and it is just few kilohertz. So modern computers are working approximately a million times faster than these early computers. And then next most important advance in previous century was that they switched from using vacuum tubes as switches inside computer to transistors. And transistor is also can be used as a switch, so it has 3 contacts. So it is silicon dioxide crystal where there is doped something else like stannum, kā ir alva in English, something else, and you have 3 contacts here. One is this emitter, similarly to your another is collector, and this is gate. And how does it work? So this silicon dioxide is semiconductor. It neither conducts electricity very well nor is well isolator. So through normal silicon dioxide current flows, but pretty badly. But you can make it either worse conductor or better conductor by doping it and applying electricity. So somewhere here you add some other atoms which either makes more electrons or non-electrons, holes of electron inside this silicon dioxide. And what happens is that these loose electrons which somehow can go through this silicon, if you apply a negative charge here, then this semiconductor becomes isolator, so current is not going through it and it is switched off. But if you add positive charge here, then they can go here through this gate and current starts flowing. So in general what you do, you use this semiconductor which is neither good conductor, neither good isolator, and you can now manage it with applied electricity that either it becomes better isolator or better conductor. And good thing is that you can make it much more efficient and much smaller than this vacuum tube. If size of vacuum tube was usually few centimeters, then modern transistors are nanometers, milli, micro, nano, so this is millions of millimeters in size. And so first, because transistors may also be used as amplifiers, they may not work as a switch, but they also may work. So you can do it in different ways. If you apply this charge here, then you may use it as a switch, like either here is charge and here is current going through emitter to this collector. So if you apply and use it as a switch, then it's as a switch, but you can also use as an amplifier. You can apply this charge gradually, and then it amplifies signal, weak signal into better signal. And of course, in all analog devices, instead of these vacuum tubes, transistors were used to amplify different signals, for example, for hearing aids, for pocket radios, etc. And later at 1960s, first integrated circuit was created. And what is integrated circuit? Integrated circuit means that you have many integrated transistors on this silicon dioxide die. So for example, here is your die, and for CPU it may be approximately 2 by 2 centimeters. And here you have many transistors put together, making different kind of operations together. And with these integrated circuits you could make quite sophisticated devices very small. And how small is then first integrated circuits were not very sophisticated. Usually you had just a few gates inside it, for example, to do and or not, etc. operations. But later, of course, more and more things were built into these integrated circuits. And for example, if you look on modern computer and your mobile phone, usually it has only one single chip for all these operations. And then you have different chip, for example, for your accelerometer, for your microphone, etc., etc. But all of these complexities of modern computers are actually usually built into one single chip. And so if you look on these integrated chips on your computer, there are not very many of them. And so starting with transistors, all these computers become smaller and more powerful, and leading company around 1960s was International Business Machines. Why it's not IBM. And they created a computer called System 360. Today, retrospectively, these computers are called mainframes, or real computers. But at that time, these were called just computers. And what was important about these computers is that because computers were expensive and you always wanted to force them to do some useful work, they supported many concurrent users from remote terminals. We will talk about computer architectures in more details maybe later, but the idea here is that there was one single computer and there were many so-called terminals, and terminal is not computer. Terminal is just a display to show you something on screen, and to send your keyboard events data back to the computer. So actual processing were happening in these big boxes, and so these were very expensive. And if you know something about different kind of codes, general manager of IBM around that time told that there are maybe market for approximately 20 computers around the world, because only largest and most rich companies could afford such kind of computers. They were very expensive. But later, another kind of computers were created called mini computers, and mini computers are still not IBM PC computers. These are somewhere in between these mainframes and IBM PC computers. One of most important probably is DEC company, which created mini computer, which was first computer used to create and develop Unix operating system. So they still supported multiple users through several terminals, but their architecture was simpler and they were actually weaker in processing power as well. But because these were much cheaper, these were much more popular, and this PDP-8 mini computer was one of computers which was used to develop Unix operating system. And for example, MacOS system is descendant of this original Unix operating system. And so after that also IBM created so-called mini computers. One of first system was that one, but there was also other kind of computers called supercomputers. And one of first companies which was famous at that time was a company called Cray. And where is difference? Difference is following, that in general all these computers I talked for now just have one single central processing unit. And for example, if there was many users working on this single CPU, what actually was happening was that they used so-called time sharing, that some data were put into this computer and put out for one user at that time, or another user at that time, or another user at that time, or another user at that time. So here is time flowing. And then it went back to that user. So what was concurrent was actually not simultaneous, but sequential operation, just with short, and this was, let's say, 10 milliseconds for each user. And if it happens quite quickly, then user may think that this computer actually supports many users all at once, even though it actually switched from handling requests from one user to another user to another user. But supercomputers immediately introduced this idea that there may be many central processing units working really concurrently, and that means they could handle much more data coming and working on these several processors. Nowadays, of course, even your personal computer has usually 4 or 8 processors inside it. But at that time, of course, these mainframes and mini computers had only one single processor, but these Cray computers had actually several processors already to do different kind of parallel computations. So that's one of important differences between supercomputers at that time and normal computers, because these were already built to do parallel computing. And then around 1970s, advent of microcomputers started, and they started with Intel 4004 microprocessor, which handled only 8 bits at the time and worked with 100 kilohertz. So remember, these computers which worked with vacuum tubes worked with around 100 Hz, maybe kilohertz, and this worked with 100 kilohertz at that time. And this processor was used to create first microcomputers, and one of first ones was Altair 8080, and it was similar to these old vacuum tube computers because its programming was done here, changing these switches to load these were general purpose computers, so you could do anything with them depending what exactly programs they loaded, but loading this program into memory was not done with punch cards, but it was done with switches. For example, you switch it first instruction and switch it by bit, like do this. Then you told second instruction, pull the switch bit by bit. And of course, some hobbyists could actually execute real programs out of it. And then you similarly entered some data, and then you got something out on this display. So in general it was calculator, not real computer, but difference was that it was general purpose calculator. You could create any program you could manage to put into it just using these switches. And then company called Microsoft was created by Paul Allen and Bill Gates, and they created implementation of basic programming language for this Altair 8080 computer. And later they also were contacted from IBM when IBM developed the IBM PC computer, or this microcomputer or personal computer. They didn't have operating system for it. And what is an operating system? Operating system is program which makes your computer usable, because if you have operating systems and loading new program inside it, it's very easy. You just say load Microsoft Word for now, or say load Java compiler for now. But if you do not have operating system, then of course you have to switch from one program to another program in much harder way. In general, that means you have to do your own manual operations to load new program inside internal memory of computer and then execute it. Maybe some of you have seen these game consoles which were connected to the TV set, so you had this cartridge with particular game, and these game consoles didn't have operating system. So what you had to do is put particular cartridge, say load program from this cartridge and execute it. But now of course you can store many programs on your hard disk and load and unload any program what you like. And so what is called personal computer is this microcomputer architecture which was created by IBM. And why it became so popular? Because IBM decided to compete with these other microcomputers like Altair and Sinclair and other kind of computers, that they should be made from general purpose hardware. So it was quite easy to create clones of it, because all this hardware was not proprietary but easily available from different vendors, mostly Intel at that time, who provided these different kind of processors and other integrated circuits and chips, and also from other companies. And then later Apple was created a company, but Apple was different than Microsoft because they decided to do both, to create hardware and also to provide software for them. And so it was founded in garage, similarly to Microsoft, by Steve Wozniak and Steve Jobs. And they created their own computer called Apple I, which was not very widely available. But later they created computer Apple II, which was quite widely usable around 1992. And there was other microcomputers which were not IBM PC compatible or Apple computers like Radio Shack, TRS-80. So all these were different hardware, so you couldn't run the same programs on these different computers because the hardware, how they work, was completely different. And some other very small, even portable computers like Osborne 1. And so first IBM PC was created an industry standard was in 1981. And yeah, so they decided that they do not have enough time to create operating system for this hardware, and they contacted Microsoft. Microsoft also actually didn't have operating system at that time, but because Bill Gates was so good manager and genius to see business opportunities, he convinced IBM representatives that they can create this operating system, and they actually bought from other company operating system called QDOS from QuickDOS, and then they improved it and created so-called Microsoft DOS out of this system. Showed just letters on screen, so these were textual terminals or textual interfaces. But then there was a company called Xerox in American English. I would say it's actually Xerox because I don't know why English should be so irregular that X at the beginning of word becomes Z. So, and this company actually created hardware to make copies of paper documents. And Xerox became as a word to create copies for something. But they looked into future and they find out that sooner or later something is wrong with my Zoom settings. I think that Zoom decides by itself to change microphone volume without notifying me. So this company actually was working into making copies from paper, but they look into future and they decided that with advent of computers, importance of paper probably will not be so important as it was 40 years ago, and they started to look how to do this with computers, and they developed their own operating system and their own hardware to work on it. But they introduced graphical interface for computers. So here again it's quite interesting about establishment. For all these real computer companies, they were okay just handling text as an input and output, just letters and numbers, etc. But for many reasons this had to be a different company, not established computer company, which decided that there could be better interface how people interact with computers, and computer should also show something else besides just letters and numbers. And so they introduced their own prototype for computer and their own prototype operating system called Xerox Star or Xerox Star, which used what you can see is prototype of modern graphical interfaces. So they introduced all these things. What you see is what you get. They introduced windows, overlapping windows, mouse cursor, right click, left click, all what is still relevant for today. And Steve Jobs visited this company, and he was very excited about graphical interface. Also, what Xerox did, they also introduced local area network, but because Steve Jobs was not so skilled to look into futures that also computer networks will be important, he ignored that thing that these computers could talk each to other through the local area network. So it was precursor for the Ethernet network. But he understood the importance of graphical interfaces. And so he created Apple computer, which also introduced graphical interface at the time, and that was first most popular one because Xerox was still in business of making copies from paper, so they were not very aggressively marketing their prototype of computer, but Apple was first who actually got the graphical interfaces to the masses. And that was in 1984, and they used this book from 1984 to use as a theme for their marketing campaign, and it was very successful. And so that is Apple Macintosh graphical interface at that time. And you see that all these important things are still used today. Resizable windows, icons on desktop, menus, etc. And then, as usual, for early beginnings of something, similarly as when cars were developed, everybody in their shed tried to build cars. So there were many hundreds of different car companies even in Latvia when there was not established large companies which could do it in scale and therefore for cheap. And similarly for microcomputers and other computers, initially there were many competing companies. For example, for mainframes, all these real computers which supported even at that time many pseudo-concurrent user. Besides IBM, there was Olivetti in Italia, Link and Uniface. For supercomputers, not only Cray, but also CDC. For mini computers, DEC and Xerox. And for microcomputers, Acorn RISC Machine in UK. So this company I will mention still because they had different architectures than IBM PC computers, but ARM now is de facto standard, for example, for mobile phones and other small devices like Raspberry Pi, etc. Then another company in Europe, Sinclair, Japanese companies like Toshiba, Hitachi, American companies like Hewlett Packard and Dell, which joined later, and of course Sony and Apple also were in business of microcomputers, which are nowadays called personal computers. So, but today, of course, what has remained, IBM actually do not produce computers at all. They are now currently business solution company, so they provide software and they work on hardware only for bleeding edge or leading edge hardware, for example, for quantum computers, etc. Cray is still relevant, it still works on supercomputers to provide these computers with very many processors or cores to work. But of course, many of these early companies didn't make it through this market because for computers, similarly to other devices, larger companies which create these devices in bigger volume, they can do it for cheaper, and therefore there are not so many companies which produce computers nowadays. And actually Apple particularly also today is not actually a manufacturing company. I say that Apple is mostly advertisement company, similarly to Nike and Adidas. They are advertising, so Nike and Adidas advertise clothing and shoes and accessories for clothing, but Apple is a company which advertises electronic gadgets, because if you will look in details, all this hardware is actually produced by some not so named companies somewhere in China. So, and they just put Apple logo on it and advertise it as a Apple hardware. They still work on software, of course. They develop iOS and macOS operating systems and applications for them. But you can't really say that Apple is hardware company anymore. So, and now a little bit about these integrated circuits. So, integrated circuits is probably the most important thing developed in previous century, because it allowed to make everything smaller and smaller and smaller and smaller. And Gordon Moore, who founded which company, I don't remember, one of these companies, I think DEC or whatever. So he noticed that these companies which creates chipsets, and leading companies, of course, Intel, of course, he was one of founders for Intel, like AMD and Intel, that they managed to squeeze more and more transistors inside the same area of this silicon dioxide die, and that this observation is approximately that you can squeeze more and more transistors almost exponentially. This means after the same amount of time, size of transistor becomes twice as small. So initially it was like 5 by 5 millimeters, then 2 by 2 millimeters, then 1 by 1 millimeters, and 0.5 by 0.5 millimeters, and now it's approximately, let's say, 7 by 7 nanometers. So that means in general you can put more and more transistors into the same chip, and that means you can create more and more complicated integrated schemas inside this hardware. And this is actually not rule, it's observation, and it holds pretty well for almost 50 years. But if you will look here on this scale now, because now it reaches physical limits, because you can't create transistor just by single silicon atom, then of course it becomes slower, and we will talk in details later. Also, more transistors on your processor doesn't mean that it will become faster, because if you look on clock frequency for processors, they are actually not changing for almost 10 years. Processor clock frequency was 3 GHz 10 years ago, and it's approximately 3 GHz for now. So it reached saturation there. But for Moore's law, it's more, it holds somehow only particularly, and Moore's law actually says how many transistors you can put into the same area of this die, but it doesn't say that more transistors means that your computing power will be greater. It means in general it's more complicated, but in general more complicated processors can do more, but again in this complexity it comes some saturation, and therefore for last 10 years you can't really say that overall performance for computers still grows exponentially, even though number of transistors for these newer processors grows exponentially. This added complexity do not directly translates into better performance. And for some other technologies. They are similar observations, only difference is that speed, how it improves, is not the same. For example, for number of transistors inside processor, it's doubling approximately every 2 years. In general, it do not affect price of computers at all. You could buy average or above average personal computer for $1,000 10 years ago, and you can buy it for approximately 1,000 years for today. It will do a little bit more than 10 years ago, but not much more, and it will not become much cheaper because, again, here we are reaching some limits how cheap something can be. And similarly, everything is improving. For example, disk speed, network speed for both local area networks and global networks for other things. But the problem is that, for example, processor speed increases faster than for persistent storage, like magnetic disks and solid-state disks. And currently, the thing what is improving the most is networks, because a long time ago, network was the slowest thing in your connected computer. Now, actually, sometimes, in many times, if you have optical fiber going to your home, your network actually can handle more data than your hard disk in your computer. So, therefore, these bottlenecks, what is slowest device in your computer, now is changing. If long time ago, slowest thing was network, now usually slowest thing in your computer is persistent memory, like hard disk. And sooner or later, of course, this exponential growth will end, because nothing can grow exponentially forever. And so here is one of smallest microprocessors you can see and buy. Of course, it is not as powerful as your processor for your personal computer. Usually such small devices are used for simple calculations, for example, RFID devices, which listens to other devices transmitting requests, that also harvest some energy from these microwave requests, and they respond back with transmitting their unique identifier. For example, RFID devices also need a small microprocessor to do these operations, and of course all of them have some quite weak for modern standards, but still microprocessors inside them, just to reply back with requests using radio waves, for example, to say what their unique ID is. And because we are handling more and more data, many of these data, of course, are different kind of bullshit and cut pictures, etc. So it's still not enough. For example, if you look on these supercomputers, which have this massive parallel architecture, they are still actually bigger than supercomputers of previous century. So they can take kilowatts of power, and they can take many rooms to locate these computers somewhere. So that's in short about history. Do you have any questions or comments? If no, then I think we can create break. And break probably should be approximately 15 minutes, so that is I may be back to my computer earlier, but But I will continue this session at 18:15. So, second part for this first session is a little bit about theory. I hope it will not be too hard for you, and if you will find it out hard, you will not need everything what I will tell you here to do your practical exercise, but at least you will need to have some understanding about number systems and how computers work. So, second part for this session is called number systems, or saying there are 10 types of people in this world, these who understand binary and these who don't. Do you understand what does it means? How 10 may be split into 2 parts. So, these who do not understand, hopefully you will understand it after this session. So, computers work. What is that? I am already sharing it. So, computers work on calculation system, what is called binary. And, for example, to represent any number, you can use many numbering systems with many choices for how many digits you have to represent unique value. For example, because accidentally our hands have 5 fingers or digits and we have 2 hands, we mostly use decimal numbering system because it's easy to count on our fingers. But minimum amount of digits or unique numbers what you need to use to represent any number is just 2. So you can't use less than 2, but you can use 2 and anything from 2 till to the infinity. And why computers work on binary? Because it's much easier to handle. There were some even electronical computers which used decimal numbering system initially, but it was found out quite clearly that creating computers which converts numbers from decimal to binary internally and then from binary internally to decimal back for people and do all calculations binary is actually better design approach than do everything in decimal system. So everything in modern computers now just work in binary, but to work in decimal system you need to convert from decimal to binary to work internally and from binary to decimal to represent it back. But because working with binary internally, for example from processor, it's much easier than to work everything in decimal system, these additional conversions from decimal to binary and back actually is easier than to do everything in decimal. And therefore all modern computers now use this binary system, which means digits which you have is only 2, 0 or 1, true or false, yes or no, on and off, call whatever you like. And why it's better? Because it's easier for electrical circuits which are used internally for modern computers. But if you do counting in general, there may be many numbering systems. So we as a people mostly use decimal numbering systems. This means we have digits or numbers from 0 to 9 to represent unique value, and then we use positional system for tens, hundreds, thousands, etc. to represent 10, 100 or 1000 times more than these individual cases. For binary, we use only 2 digits, 0 and 1, and everything which is 2, 4, 8 or 16 times more, we use more and more digits to represent positionally these 2s, 4s, 8s, 16s, etc. But problem with the binary system is that it's very verbose. For example, what is 10 in decimal system is to be exact, we will do it in following. In binary is 1010. So you see that it's approximately 2 times longer than in decimal system, and that's the biggest headache to use binary system directly, because all numbers become very long. And what you can do about this, we can group these bits together in different groups, and we can represent groups of digits with something else. And what are leading other standards? For example, you have 0, 0, 0, 1, let's say 0, 0, 0, 1, 0, 0, 0, 1, 1, 0, 0, 1, 0, 0. So you can group these numbers in different ways. One way is, for example, you assign specific value for all these groups of 4, like 0, 1, 2, 3, 4, 5, 6, 7. Then you use octal system. And if you have larger digits, of course you need to pad it, for example, with leading blah blah blah. For example, 1 1 1 1 1 1 1 1 in binary is 7 7 in octal system. Or you can group it even more. For example, these 4 together with these 4s, and then you would have 16 different digits. How can you represent 16? So somewhere here you go till to 9. But what comes next? And they decided that it will be A, B, C, D, E, and F. So it starts with 0, 0, 0, 0, 0, 0, 0, 0, and then 1, 1, 1, 1, 1, 1, 1, 1 is letter F for this numbering system. But and sometimes you can use other counting systems, I will explain later. And how you usually group these binary bits together. De facto standard is 8 bits together, which is called byte. In some systems it's also called char, for example in C programming language. But de facto standard how we call is 8 bits together is 1 byte. And because 8 bits together, actually I was wrong here about this A, B, C, D, E, F, because what you actually can represent them is not full 8, but I think 6 bytes. So for all 8 bits you need to represent with 2 letters, and I will explain it. And then there are mismatch between what you call so-called word. Proper thing to call word is usually what your computer can handle at once. And what means handle at once? When you get some input here, neither of computers is so stupid that you say read only 1 0 or 1 1 at once. These are some external devices, so-called serial devices, which may provide it, but usually even these serial devices provides it in groups of 8 bits or 1 byte. But usually all computers can handle many of these bits at once, and early computers usually got 8 bits at once, so this means 8 parallel lines of inputs where signal is either high or low, representing either 0 or 1. Then 16 bits at once, then 32 bits, 64 bits, and 128 bits. So most of modern computers now have processors which can handle 64 bits at once or 8 bytes at once. So large number can be taken as an input to central processing unit and done something with this. And of course, if you deal with actually much smaller numbers, then that means these lower bits have some value like zeros, ones, and everything else here is just 0, 0, 0, 0. And if you have experienced enough and you switch it, for example, for new version of Microsoft Windows, and I think either Windows 7 or Windows 10 was first which introduced 64-bit operating system, and all the files mostly become twice as large. Why? Because they didn't do great optimization to compress this data, so that even if you need to store values like from 0 till to 8, but you start using hardware and operating system which works with 64 bits at once, your data stored and read from hard disk is still much bigger, because this is smallest amount of data your processor actually handles. Of course, there can be done some optimization which allows you to store 8 bits more compact together, and they are padded with these meaningless zeros bits together in central processing unit. But if such optimization is not done, then when you switch to more powerful processors, all your stored programs becomes bigger, because this is the minimum number or value they can store, read, write from external memory in the hard disk. And so what does it mean? You can always deal with smaller numbers, but then, for example, if you need to get precision with 128 bits of some larger number, you need to do it how many times? 32 times. But if your processor can handle all 128 bits at once, then of course it needs only one operation. So with smaller CPU, to handle 128 bits, you need to read 8 bits, handle them, then read another 8 bits, handle them somehow with some previous results, and do this 32 times and you get result. But if you can handle 128 bits all at once, you just read, calculate, and result is ready with just one operation. So that means in general, as more bits your hardware, your processor can handle, as it is more powerful. In practice, it's not always true, because your program may be written so stupidly that it actually do not use all these features of processor. And what is actually happening is that you use your very powerful computer, but you still use only, let's say, 8 bits from this large number and do it 32 times for calculation and then provide result, where again everything which is meaningful, it's only 8 bits here and everything here is just zeros in this larger number. So in practice it doesn't mean that your system becomes much more powerful, because these features of your hardware may not be used by your software. And so you can represent these numbers in very different ways. For example, non-positional system, like just sticks carved somewhere, or Roman numbers, which are also not, they were a little bit positional. For example, 6 and 7, or 4 and 6 are using positional system. For example, add 1 to 5 or remove 1 from 5, but it's still not fully positional, so you can't do good arithmetics, for example, for adding, subtracting and multiplication, etc. But if you use positional system, what these digits represent here, of course, depends on what kind of numbering system are you using. So now about larger numbers. I think that nobody of you gets confused how you work with decimal system when you write larger numbers than single digit, then each number going to the left means so many times more than you have your numbers in total. For example, last position means from 0 till to 9. Second to last position means from 0 all till to 9 tenths. Then next position means from 0 till to 9 hundredths. Then from 0 till to 9 thousandths, etc., etc. And when you write 527, this means 5 times 100 plus 2 times 10 plus 7 times 1. And similarly, you can represent numbers in just 2 digits, zeros and ones. And for example, here is one number in binary, 11011101, and then you need to add another number, 101100. And what do you do? Because it's positional system, you just still add them. And in this particular case, when you have only 2 digits, what adding means is actually AND operation. For example, there are operations. I have lost some. Not here. So, particularly if your values for these digits or numbers can be only 0 or 1, adding and subtracting actually can be described as so-called logical operations like AND and OR not. In general, if you look on computer science and in this logic, you can build any device which works with Boolean numbers using only not and AND operations or not and OR operations. And everything else you can do as a sequence of these two operations. And in early computers, actually, they provided these integrated chipsets with so-called NAND and NOR operations, because with not and not OR operations, you can actually group them together and provide any other logic. But how does it work? So not means following. You have one input and one output, and if you look how it works in electricity, it's something like this. So here is your negative power line, here is your positive power line, what is powering device, and you have just switch, which is closed by default, but if you apply signal to it, it opens. And so here is your input, and here you can measure your output. For example, and you can provide to input to the next device, and then input to the next device. And so what is not shown here is how you power up these devices. So all of these devices should be powered by direct current, and then this output goes back to the other end of the current. So, but if you talk only about logic, you just ignore it because you already know that everything should be powered up. So if you have no signal, it provides signal, so this means low voltage here, high voltage in the output, high voltage in the input means low voltage in the output. And for other operations you have at least two numbers, like AND means that it has output only if both inputs are high value, OR means that output is a high value if at least one of them is output. And exclusive OR actually may be emulated by some of these operations. It means it has high voltage if these are different. And so when you calculate these numbers, in general, in decimal system you need to count, for example, how much is 3 plus 7 or 2 plus 6 or whatever. But in binary operations, in general it means just AND. So, and when you calculate it, what you need to check is put together these values. Actually it's not AND, it's OR and carry bit. 0 plus 0 is 1, 1 plus 1 is 0, sorry. So you write ones if there is at least ones, and if you have two ones, you need to carry this bit, and the next one, similarly as you carry this number, when you add, let's say, 4 and 7 in decimal system, so it's 11. So you write here for this 11, and you carry next bit for decimal system here, and then you again add this to that. This means 1 0 in decimal system, you carry bit here, add here, carry bit here, etc. So all these are just actually Boolean operations. You don't need to count like from 3 to what means 3 plus 3 or 4 plus 2. You just need is this and that together 0 or 1 or not. And similarly, for example, when you need to multiply it, and for decimal system you need, for example, multiplication table from 0 till to 9 at least. Of course, if you are better than that, you know something from 0 to 20, by 0 till to 20. But for binary operations, again, all your multiplication table is from 0 to 1. so only 2 digits. And again, you just do positional multiplication, and 1 by times 1 means 1, 1 times 0 means 0, 1 times 1 means 1, 1 times 1 means 0. And what is times is actually ANDs in this case, or AND operation. You have 2 inputs. If both are 1, it's 1. If one of these are 0, your output or result is 0. And then here you multiply everything by 0. It is just 0, 0, 0, 0 4 times. And again here you multiply by 1, which means 1 times 1 is 1, 1 times 0 is 0, and that means it's AND operation in Boolean logic. And then when you do compute total sum for this, again you use actually OR here and carry bit operation. So that's how you do, for example, arithmetic operations using just switches, which may be output may be either up if everything is up in input, or just some part of it. And of course you will not be required to do binary operations in your head, but what you should know is, for example, that when you use some calculator here, that all these calculators has extended options. For example, for programming or extended one. And then you can, for example, switch to different counting systems for your numbers. By default it's decimal. And for example, you write 333 here. You see here, for example, how it is represented. And you can switch bits on and off here by clicks and see how it's represented in decimal number system. And here it is represented in binary system. So, and then you can do similar operations when you group bits together, for example in octal system or hexadecimal system, but it is not required for you to know. You just need to know the principle that you may use different numbers to count these things, and then you use just positional system to represent these numbers with different lengths. What sometimes is needed for you to know is, for example, how big is range of values which you may represent with different numbering systems, and different lengths of these numbers. For example, it is very useful to know when you work with computers that you know power of 2's. And I can easily say powers of 2's till to a few thousand, like 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 2096, and then I don't know. Why? Because sometimes it is useful to know approximate range, how many digits you need to know in binary system, because, for example, there was quite many attempts to do electronical polling using computers, and in Netherlands, they had used computers to do electronical voting. And what they found that for one particular place, there was too many of votes counted into computer. But they just find it out by accident, because this was not very big polling station. It was expected that there would be only few hundreds of the votes, but they got few thousands of the votes on that computer. And what they find out that when they recounted all these votes again from all the votes, and what computer showed that there was 4,096 more votes in computer. So something like they expected like 200, but they get, let's say, 4,296. And what is important about this 4,096 is that in binary representation, number is 1, 0, 0, 0, 0, 0, 0, 0, 0, 0. And what they find out was that probably computer just got glitch in its calculations, and this single bit was switched from 0 to 1 accidentally. Usually it doesn't happen. It shouldn't happen because there are some built-in internal checks in hardware, but they didn't have additional checks for software to check for that, like for example hash sums for all the values, what Git version control system does, or Bitcoin money does, etc. And because of this particular number in decimal system, they find out that probably only just once this single bit got error on these calculations, and because of that they got 4,096 more votes counted as casted in this particular area. And that means that sometimes you need to know, for example, what are these round numbers in binary system. In decimal system, round numbers are these who ends with zeros. In binary system, round numbers are also these which ends with many zeros. But of course in decimal number it is not so round. Of course it's always even number because it divides by 2, but you can check, for example, what are these round numbers in binary system. And so with one single digit you can store only 2 values. With 4 bits you can store 16 different values, with 8 bits 256, with 10 bits 1024. And nowadays I think it's more or less organized and ironed out, but because 2 in power of 10 is very similar to 10 in power of 3, or 2 times 2 times 2 times 2 times 2 10 times, and 10 times 10 times 10 is very similar. In early history of computers, when it was less organized, they mixed up these binary, rounded binary numbers with decimal numbers. And at that time, computer users know that all these computers will show how much hard disk memory has, how much random access memory it has. It's not very precise because sometimes they used powers of 2 or 224, and sometimes they used precise 1000. But nowadays it is organized because they use this prefix E from no idea. No idea why it's E, but if it says that it's 1 kilo with E, this means kilo in binary system are 1024 or 2 in power of 10. And similarly, if it's 64 key with I here, it means it's not actually 64,000, but it's actually 65,536 in precise decimal number. So don't be afraid about this. Where I can show it, for example. For example, for modern computers, you may find out here that it shows that my swap file to swap out something from random access memory to hard disk is 1 giga, but not in decimal number, but in these binary numbers. So this means in decimals actually 1024 times 1024, or you can calculate it out. Or this, so it's not precise billion, but it's 1,048,576, and of course in binary you see it is very round number. It is 1 0 0 0 0 0 0 0 0 0 0 0 0 0 0. So don't be, and all modern systems which care about this, they actually show, and then it's very precise number. It's not something around 1,000, maybe more, maybe less. It's precise. So that's about these things. Now about things how you write these numbers. So you can write these numbers. If your numbering system is smaller than decimal system, we still use decimal numbers to represent them. For example, if our base, how we count for each particular position, is 10 digits, we count from 0 till to 9, and of course 10 means we carry out this digit to the next position here. So actual digits are from 0 till to 9, even though total number of them is 10. If it's base 2 or binary system, it's just 0, 1. If it's base 8 or 3 bits grouped together, then we can represent it with from 0 till to 7. And if it's base 16 or 4 bits, then we can represent it from 1 till to 9, and A, B, C, D, E, and F. So this is called hexadecimal. It's not very proper way. It actually should be called decimal, but conventional way to call it is following. But problem here is that in base 16 we can actually represent only 4 bits from zeros till to 4 ones. So that would be 0 in hexadecimal and F in hexadecimal. But we usually organize bits not only by 4 but by 8. And so minimum amount of 8 bits together is 0, 0, 0 and 1, 1, 1, 1. And how can we represent them? And in most of cases we represent them just by two letters here, an F and F. And for beginners, this may be very big confusion, because when we talk about byte, for example in programming languages, etc., values of these bytes are represented by two letters, starting from 00, 1, 2, 3, 4, blah blah blah, till FF. But all these two letters actually represent one single byte or one single number. And that may be very confusing, that what you consider just a single number is represented by two letters. And if you look on theory, so it is how many values byte can represent. It is 2 in power of 8 or 256. This means from 0 till 255. And you represent them in two positional numbers, like 16 times from 0 till to 15 represented as a F, plus 1 times 0 till to 15 represented as a letter F. So we need two digits or two letters just to represent value of one single byte or 8 bits. And because of that, there are specific editors which deal with this problem, because if you look on actual values here, and these are actual values represented just a dot here, because they do not have graphical representation for these values. But I have 16 bytes here saved into this binary file. But it is, these 16 bytes are represented by 32 symbols, because one byte or 8 bits needs 2 symbols, another needs 2 symbols, etc., etc. And therefore you need these two different views. One view where one single bit is represented as a one particular space or place to hold value, and another view where you need twice as more characters to represent these values. And that of course has a problem, because every time, for example, when you use internet and send emails, etc., everything here is actually text-based. Even if you send some binary data like digital images and sound through email or your Word documents, these are internally represented as letters. So internet mostly is based to send telegrams using numbers and letters, or in general both together called characters, from place to place. And that is problem, because if you need to send just one single byte through your email, you actually need twice as much bytes to send, because value of this byte is converted into letter representation, and in letter representation you have actually two letters representing just one single letter in actual data. So that means every time you send something, you would need twice as more data sent through the network. And how can you do it more efficiently? More efficiently you do so-called base 64 encoding. And any time you see some abracadabra, probably you have seen something like this in your life already. So what do you see? You see upper lowercase letters, numbers, and some specific marks like maybe underscore, maybe slash, and sometimes equal sign at the end. So this is another numbering system which is more efficient than hexadecimal representation, because here I see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So here I encoded 12 bytes or 12 characters with this system, and it is not twice as long, but it is a little bit longer. So this is one text encoded with another text. And how this base 64 works? Base 64 works in such a way that if we look on characters which we can represent in computers, that means letters together with numbers, we actually can use approximately 64 different kind of numbers. So base for our calculation is 64, not 8, not 16, not 128, but 64. And 64 is not power of 2, because every time you make something twice as large, then it is in power of 2, but it's only 6 bits. And for example, here I have encoded 3 different bytes, letter M, letter A, and letter N, which together are 24 bits. But in this base 64 encoding, you can represent 6 bits with particular digit here. And by digit I mean these lowercase, uppercase letters and numbers. But because these are not divisible by 8, so that means I need 4 letters to represent 3 letters here. And that means if sometimes I will have, for example, only one single letter here or 2 letters to encode, here I will have some empty values, and these empty values are represented with these equal signs. So if it divides precisely, then I don't have any space filled up with equals at all. If it doesn't divide by 6 nicely, then I have 2 equals here or just 1 equal here. And another problem with this encoding is that because it's not aligned to actual values of these bits inside bytes, if you start counting these letters from some other places, it looks completely different. For example, here we see this string SVG, blah blah blah, but if I have some character here and encode it, I don't see this SVG anymore, because these values are grouped by 6 bits, not by 8 bits. So this is not encryption, it is just different representation of values which you can represent with alphabet or numbers with lowercase, uppercase letters and 10 digits in total. And if you see something like this, which looks like an encryption, you can just use any public service here and say the code. Where is the code? The code. And we get this initial text back. So it is not encryption system, it is just another way how you can represent values of these bits in more efficient way than you use in hexadecimal system, when you need 2 letters just to represent one single letter as its visible value. And then, of course, problem may be how can you represent actual all possible values for 8 bits in one single byte. That means values are 2 in power of 8, or total values are 256. And there is no standardized numbering system how to represent these numbers, but there are some ideas how can you do this. And these ideas are following. First, if you think that remembering 256 different digits is hard, remember that Japanese and Chinese still use hieroglyphs and they need to know at least 10,000 of different characters. At least few thousand, for example, to be fluent to read them. And so learning 200 something probably may look hard, but it's not that hard. But general idea here is that if we look on our decimal system, we use positional system that if we need to write large number, we use positional system. So here are ones, here are tens, here are thousands, here are 10,000s, and then we write how many ones we have, for example, how many tens we have, how many thousands we have, and how many 10,000s we have, etc. with these numbers. So that's nice, because if we use positional system, all these calculations are not easier done by hand, but also easier done by computers. But what is not positional is how we decided what these numbers represents here. For example, 8 looks much more filled up number and heavier number than 9. And for example, I do not know, 6 is much more filled up number by 7. So if we look on order, how we order these digits inside numbering systems in itself, it is not positional. So it is just a historical accident how we decided to represent these values. But these ideas how to represent these numbers in base 256 is that to make remembering and understanding easier, these also digits themselves are positional. An idea here is following, that you need to represent 8 bits somehow, and 8 bits can be only on or off. And you organize it in some manner. One manner would be like this. So here is placeholders. Actually, I will write it in different color. And then you just fill up this single bit or not. For example, if you want to say it's 0, you fill up 0. And so this means 0 in decimal. If you need to fill up, and then you can say, okay, this is 0, this is 1, this is 2, this is 4, this is, let's say, 1, 2, 4, 8, 16, 64. And this is placeholder for 64. So if you look on this calculator here, these are these bits. You put either 1 or 0 here in particular place. But to make these digits nicer, it's not just not long string of zeros and ones, but it's some position of bits either switched on or off. And so if you need to say 1, then you say this is your 1. If you want to say it's 2, this means it overlaps and fills, because you can say either 0 or 1. This is your next position, so this is this number. If you say 3, it is 3. If you say 4, it is now this number. And what is good about such positional system? First, that calculations are absolutely easy to do with positional numbers. For example, if I have this number and I need to add that number, what is in total? You just do these AND operations in Boolean logic. Here is 0, here is 0, it's this, here is this, and here is this. And when you check, for example, what this number is, it is 4 plus 1 or 5, and here is 1, here is 4, and of course 4 and 5 is. So you just add these single bits as a sticks together with, so your adding table is very simple for such digits. You just check and add these single bits, and of course if you add numbers with AND operations, you need to carry out bit to the next level. For example, if you need to add, let's say 4 with, let's say 2, then okay, let's say 4 and 4. So you need to add, you definitely know that this will be put together, but because it overfills, you need to say that it needs to be carried out to the next bit. And you get, for example, digit something like this. So you add this, and you carry out to the next level, and you got, for example, 2 stripes. And only problem sometimes here is that not all numbers are easily readable, and they need to be somehow connected together, that all these digits you represent are closed shape, that, for example, when you write them, they are not mixed up with 2 different digits. And one idea here is, we published actually this idea with one of my Doombeaders, with other enthusiasts, in such a way when each bit is actually represented just by stick or line, but sometimes it is a little bit hard to be readable. So for this proposal, everything is absolutely positional, except, for example, zeros, etc. But for readability, here is another proposal which is not absolutely positional, but everything is put around this single stick, and then you extend it either to right or the left. For lower part numbers, you have these bits a little bit differently. So this loop actually is still single bit, like second bit filled up with this loop, or third bit filled up with this loop. But what is better for such system is that readability is a little bit easier, because with these different patterns it's easier to understand what these numbers represents, because they are not so monotone and they have more unique shapes. So, and it is not standardized yet, but so there are ideas how to represent such number just using one single number for value of single bit. And yeah, before we go forward, do you have any questions or comments so far? At least one says everything is good. Okay, so far I described everything only about numbers and about so-called integer numbers, no fractions, no signs. But of course, computers have to work with other kinds of numbers, like negative numbers, like numbers with fraction, etc. Then everything here again is converted just to bits. So if you look in your computer, you still will see some bits either filled up or not filled up, because that's how computers work. But what is difference is what is actual meaning for these bits either switched on and off. So if you look, okay, it's almost 8 bits. Let's remove that. So you may look on these 8 bits and say, aha, I know, it represents a number in value starting from 0 till to 255, but actually these bits may represent something else if you look on metadata, how exactly you store these values. And so, how exactly you can store these values? First, we need, for example, to know how we can represent letters. On letters, representation of letters is already standardized. And it follows from American Standard Code for Information Exchange. For early computers, like these IBM mainframes, they didn't use ASCII standard, they used EBCDIC or whatever it was called. But we can ignore them because probability is very high that probability is very high that you will not work with mainframes. But for all microcomputers and their similar clones, etc., their representation system for these values of single byte or 8 bits is standardized. And so here we see values shown in decimal numbering system from 0 till to 127 and from 128 till to 255. Here it is in hexadecimal notation and octal notation, and of course in binary notation it would be much longer. And then here is meaning, and you see that here starting from 0 till to 31, actually they do not have graphical representation. For example, if I open some editor, how could I put it? I cannot. Okay. So on here I can write these values by hand, like byte 00, 01, 02, 03, 04. And here it shows graphical representation of values of these bytes. And you see here that it just shows dot, 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 because these small values were reserved for different kind of management of computers and networking, etc. They do not have graphical representation to put on screen. For example, and if I save it, I say print it out on my screen, I don't see anything as an output, because and for example, I see that the length of this, I think, is this one. Let's make it longer. So I'm looking on chat here. In your practical exercise, you will need to do some very simple operations, probably with some binary data, just for fun. But as I told you, if you will have some previous skills and knowledge, you will be able to do this practical exercise in just few minutes. If not, first you will need to get knowledge how to deal with these things. So, and here we see that I added some value of this binary data, I think this one, 80, in hexadecimal notation, which was represented, and it was represented as a broken symbol on my screen. This means some unknown but still printable character. And then there are some values which have graphical representation. And this starts with decimal values starting from 32. It is space symbol, and then exclamation mark, blah, 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 blah. And that's how we can actually write, for example, letters in unformatted text mode, etc. So, for example, let's delete all these ones. And I write something like 20 in hexadecimal, then 21, and save it. And voila, I got printed output. And of course, I may open it, this file, with different editor. And I can just write. And then I see that these values have graphical representation. For example, these Latin letters here. So that's about Latin letters and numbers, and then they go till to value 125, and because I'm looking on this table, it means you also don't need to know everything here in your head, but I have some colleagues who need to program in lower level programming languages, and they are actually pretty good at knowing what actual value is, for example, for these letters, but you don't need to know them. And you see that here it goes still to value of 127, but these 8 bits can hold value still to 255. And here problem is that these values, starting from 128 in decimal system till 255, are not so well standardized. These may represent, and this is so-called encoding system. So all encoding systems are compatible with this ASCII system to represent values of bytes starting from 0 till to 127. But larger than that is not so well standardized. And if you see something garbled, for example, only some Latin text and, for example, wrong non-Latin characters, etc., this means your application, your program, didn't understand very well what encoding system was used to represent non-Latin letters and other non-Latin characters like Arabic, Russian, Chinese, etc. So, and that's about these ASCII letters. So, about de facto standard for modern computers to represent non-Latin characters and everything else is standard called Unicode. And Unicode is famous with their emoji. And Unicode system was introduced how you can represent approximately 16 million of different characters. And character means one sign which represented as a single unit. This may be Chinese character, Japanese syllable, or Arabic syllable, etc. And it actually may be extended even to more than 16 millions. And because 16 millions is pretty large number, therefore one of their extensions is to add different kind of emoji in the standard, how you can do all this crazy stuff different applications are using. And these emoji are not pictures, these are still characters which have graphical representation for just some bytes. But what is important about Unicode is that in Unicode one single character may be represented with more than 1 byte. So if you write something like in character map, and we can, for example, Cyrillic letters. And here what I see on screen are 4 Cyrillic letters, but if I save them, in my test file, and I look internally how it is looking inside computer, I see here that I have much more bytes than visible characters on screen. Why? Because in Unicode encoding system, these Russian letters are represented not with just single byte or 8 bits, but 2 bytes or 16 bits. And for example, here in character table, you For example, when you look in more details, you see that and we usually use UTF-8 encoding. This means in hexadecimal value, small letter e is D0, B5, and D0, that is this letter. These 2 bytes represent just one single Russian letter. And similarly, if you go into Chinese letters, oh, it's Mandarin, I don't know. Or something like this. You see that, for example, this particular single letter, what we see on screen, actually takes even 4 bytes to store inside file. For example, open it with, let's do this. So here on screen I see just one single letter, but if I open this file, I see 1, 2, 3, 4, 5 bytes, probably line break at the end. Yeah, this is line break. And these are 4 bytes for one single letter. So that's... And here I'm not talking about formatting like bold, italic, etc. It is only about extended table, which is standardized by this Unicode consortium for other different characters. One of fun parts may be following that somewhere in Twitter, and I do not know how many of you are using Twitter, but for Twitter you may see that somebody somehow got bold letters or stroked over letters inside their tweets or their profile. And you may wonder, how can you do this in non-formatted text? But there is actually specific Unicode letters, which are Latin letters with specific marks. So here we can write hello, and here it provides different kind of styles like bold or italic, but if we copy paste it, and I see this italic here, that would be normal hello, and that is this italic hello. So here formatting is not applied as a specific markup like in HTML or whatever, but it's actually completely different character. Maybe we can analyze it here with character map. So see here, first it is represented by 4 bytes, not just single byte, and this value is blah blah blah, F0, 9D, so, and it is italic capital H, and if we look on our binary editor, so here is this normal hello, here is line break, and here is this F0, 9D, this value of 0, 9D, 90, BB. So these 4 bytes represent this one hello italic style text. And similarly you can convert it to bold, etc. So besides this emoji, there are quite funny formatting applied to different Latin characters, and similarly you can generate striked out text or whatever. So yes, so some of our questions. Latvian diacritic marks also needs more place. For example, so here I have wrote this with just Latin letters and with diacritic Latin letters. And if I look on it with this binary editor, this one. So here I see that these are standardized Latin letters from this ASCII code table, but long letter E are these 2 bytes, C4 or AB. And here is N somewhere, and here is S somewhere. And again, you can search for them using your character map. Where is my character map? You can search for E. Oh, it's not highlighted. Ah, here. And we see how this character is represented. And by default we use UTF-8 encoding, so these are 2 bytes with hexadecimal value C4, AB. And that's what we see here, C4, AB. And of course we can encode it in different format. UTF-16 still takes 2 bytes, but values of these 2 bytes will be completely different, not C4AB, but 0, 1 and 2B. And then for much more fun we can do, it will not be required for your practical exercise, but there are non-canonical ways how you can represent diacritic marks for Latin text. How it's in English, garumzīme E, karon, makron, makron. What you see here on screen is the same surname, and it looks completely the same. But what is happening here is that one of these Latin letters is encoded actually in completely different way. So here it is CC84, and here is C4AB. So if we will look what CC hexadecimal number is in ASCII table, is this is just normal letter E, but it is combined with another diacritic mark, which is this colon on top of previous letters. So there are some of letters which doesn't take space, and they are shifted to the right or left depending on writing system. For example, here in some other editors which are not using Vim, I see that here in one place is taken by actually two different characters. And one is normal character Latin E, Latin small letter E, but another character doesn't take any space and it is shifted to the left. So I add this combination of bytes, and when it is represented on screen, then two different characters combine one character together, normal Latin letter E with this colon on top of it. So it overwrites previous symbol, here what I see on the screen. So, we can talk in more details about text, but some of you are already confused enough. Now I will touch also numbers. And numbers are also, there are conventions how you present numbers in computers. And leading system is following. That first you need to decide how do you represent positive and negative numbers, and de facto standard is following. That if you look on these values from 0 to first bit, maybe either 0 or 1, and if you set to 1 it means it's negative number. So far so good, and then everything else is just actual value. In positional system it means if it's 1 and zeros here it's -1, if it's 1, 1 here it is -2 and 1, -3, etc. But such very simplified approach makes problem, because it means there are two different zeros. There is positive 0, where first bit is 0, and everything else is 0. This is +0 then. And then there is negative 0. If here this bit is 1 and everything is 0, this is -0. And of course all arithmetic operations becomes much more complicated, because when you, for example, add -3 plus 2, because there are two zeros in between, you need to add +1 at the end, because you go through this positive 0 and negative 0, etc. And therefore for negative numbers, leading standard for this representation is a little bit different. That -1 is actually 1, 1, 1, 1, 1, 1, 1, 1, 1. And then you increment it by 1, for example -2 is a little bit smaller than that, 1, 1, 1, 1, 1, 1, I0, something like this, etc. So if you look on Wikipedia, it was not substituted by 2. Complement, not substitute. So, leading standard, how negative numbers are represented is following. That first of bits represents negative sign. Yeah, I think I was correct. So, for example, if your number here, 8 bits, do not represent sign, you can represent value from 0 till to 255. If it is signed number, then it is from minus 127 till to plus, actually 128 plus 127. So, and minimum number is following, maximum number is following. And again, you will not need to know this for your practical exercise, but it may be useful to know also how everything is represented with just primitive, or this means undividable numbers in computers. And then, for example, you also need numbers with fractions. And you represent numbers with fractions in so-called scientific notation. Again, if we use only 8 bits for these numbers, first is sign, so 0 means plus and 1 means minus. And then you have this power and then value. And depending on what kind of number it is, some of more bits may be represented like a power. This means in scientific notation, for example, you may write 101 like a 1.01 times 10 in power of 2. So this part goes to some bits here. For example, you write 2 here, that would be in binary system 1, 0. And this 1.01, somewhere here it says where comma is, and then you write 1.01. Of course, 1.01 is in decimal system, blah blah blah, some bits here. And because of that everything is also is floating point number represented in actually fixed lengths and fixed precision numbers. Only difference is how big precision is. Then you can always get confusing results for some of calculations. And for example, I can't find this interesting tweet, but idea was something like this. So you know this. Please prove that you are not a robot. And you need to do something like this. Please tell what is 2 times 3. And here is value. And of course humans would write 6. But computers may write something like 5.999999967. And of course when you round it up it is approximately 6. But for floating point numbers there is always some fraction part which may be actually different, because for all these possible non-round numbers you always need to add this value to single bit, which is either 0 or 1, even though you have very many bits. So this means it might be very precise, but sooner or later you need to decide, is this single bit 0 or 1? This means it either moves up or moves down actual value from this theoretical value. And with that I think I can finish the second part about these representing numbers in computers. Did I answer to everything written in chat? So, one of questions is where we are going. We are going to do a little bit more advanced things in computers. I hope that everybody of you know how to use like Microsoft Windows operating system and Microsoft Office applications. But in this particular course I will try to teach you and you will try to learn how to do some advanced things with computer, and mainly it will be to know a little bit more details about how computers work. And in next week I will describe you one of your practical exercises which will be related with representation of data inside a computer. Then I will teach you something about network applications, and again something more advanced than you know already, like using Facebook, TikTok, Twitter or whatever. But for example, how to understand what is wrong with connection to internet. I hope that I will teach you where is difference between internet doesn't work and my connection to internet doesn't work. Then you will need to do something with multimedia, a single picture, like probably I will show you difference between vectoral, graphic and bitmap images, something about sound, editing sound file, and some theory what you need to know, and something about video. And usually I will not try to show you only these practical exercises, just use this, because that's what you already probably have learned in your secondary school. But we will also discuss how this actually works, at least from user's perspective, to know, for example, when some kind of errors comes up in all these either networked applications or multimedia applications, because all these possibilities are limited and constrained by how computers handle data. And hopefully in next week, when I will explain you first exercise, you will have better understanding where we are going. But in general, it will be something like more advanced computer usage, like beyond Microsoft Office. That's what I would say. So I will take that you know either LibreOffice or Microsoft Office already, so that's considered granted. And so we will go beyond that, how you can use some other applications which are maybe needed for you these computers. So did I answer to this question where we are going? So large blocks will be a little bit about these binary data, a little bit about networking, mostly how to understand and troubleshoot your home network, what is wrong with this, because in most of the times something is wrong with your computer and your connection to the internet, not with internet, and then about multimedia. Probably about multimedia it will a little bit overlap with some other courses, because some of you may attend some multimedia oriented course already, but you will find it out. Any other questions or comments? Official curriculum says that you also need to do some kind of intermediate theoretical knowledge checks, but I will find out, is it legal to do it following that to get any successful rating to finish your course, you will just need to do your practical tasks, and you will get something between 4 and 7 only for practical tasks. And then if some of you will want to get better gradings than like 7 or 8, then you will also need to do something like exam at the end to defend your knowledge better about these topics what will be covered during this course. So in general, I will not try to make your life very hard if you want to get just through this course, if you want to get just average rating for this course, just to get it done. But also, this I will also explain probably in next week, when I will know where exactly these one more thing.